Today we are talking about the network layer, which is Module 8. So your network layer provides services to allow end devices to exchange data. So we're either talking about IP4 or IP6, IP standing for Internet Protocol. The network layer performs four basic operations. It addresses your end devices. So end devices, again, must be configured with a unique IP address for identification on the network. It encapsulates, or encapsulation, which is network layer encapsulating the protocol data unit from above, which is a transport layer, which is a segment of information, and then it encapsulates it into a packet of information. So in this encapsulation process at the network layer, the source and destination IP addresses are added. It also does routing. So routing provides services to direct packets to a destination host on another network. The role of the router is to select the best path and direct packets toward the destination host in a process which is known as routing. And then de-encapsulation, again, we've talked about before. This is getting the packet at the destination address and unwrapping it. And as long as it looks like a good piece of information, it is sent up the stack to be processed. Now, IP encapsulates your transport layer segment, the layer just above the network layer. IP can use either IP4 or IP6, and it will not impact the layer 4 segment. So remembering, anything that happens at one layer does not impede another layer. Doesn't mean they don't interact with each other, because they certainly do. An IP packet will be examined by all layer 3 devices as it traverses the network. So, however many routers this packet has to go through, at each step along the way, the router will de-encapsulate to find out what destination IP is enclosed, and it then re-encapsulates for complete encapsulation. The data portion of the packet, that is the encapsulated transport layer PDU or other data, is unchanged during the network layer process. So IP is meant to have very low overhead. It provides only the functions that are necessary to deliver a packet from a source to a destination over an interconnected system of networks. The protocol was not designed to track and manage the flow of packets and may be described as the following. It is connectionless, meaning there is not an established connection created between source and destination before data can be sent. It is referred to as best effort. IP is inherently unreliable because packet delivery is not guaranteed. So unreliability means unreliability means things like no connection establishment, no sequencing, so no sequencing if we go ahead and segment a larger piece of data into smaller pieces. No resending of lost packets. Okay. Okay, so that is the unreliability factor of best effort. It does not mean that it does not operate, it certainly does. It is also media independent, meaning that process is going to happen regardless of whether we're using copper, fiber, wireless, satellite, whatever type of medium is carrying the data from point to point. And as you can understand, even without being networking gurus, that type of media is going to change from point to point. So IP is considered connectionless, meaning, again, it does not establish a connection with the destination before sending the packet. There is no control information needed, so there's no synchronization, there's no acknowledgments, nothing. The destination will receive the packet when it arrives, but no pre-notifications are sent by IP. If there is a need for connection-oriented traffic, then another protocol will handle this, which is typically TCP at that transport layer. So it will not guarantee the delivery of a packet. It has reduced overhead because there is no mechanism to resend data that is not received. It does not expect acknowledgments. It does not know if the other device is operational or if it can even be reached. So it says, oh, hey, I have this packet. Let me check the destination IP address and let me shoot it in the direction of the destination, period. Unreliability. It cannot manage or fix undelivered or corrupt packets. It cannot retransmit if an error occurs. It cannot realign out of sequence packages or packets. It must rely on other protocols for these functions, which is why you see TCP coupled with IP for reliability. It is again also media independent. It does not concern itself with the type of frame required at the data link or the media type at the physical layer. It can be sent over any media type, copper, fiber, wireless, etc. And of course, there are other mediums out there. These are the three that we concentrate on for your studies. And as you can see in the depiction here, it can start at a local area network, which we should know by now is Ethernet based. It can go through a serial connection using a copper serial connection. It could then go through a fiber connection back to a copper Ethernet connection, and then at the actual destination through a wireless connection. So each point, the NIC prepares and gets the information ready for that point-to-point transmission. That is that encoding and decoding that we brought up previously. There is, however, one major characteristic of the media that the network layer considers, and that is what we refer to as the maximum transmission unit. The network layer, again, receives this from control information sent by the data link layer. So think back to when we talked about the data link layer, and we talked about that logical link control layer that speaks to the layer above, which would be the network, and also the media access layer that spoke to the layer below, which would be the physical. So this would be a functionality that you would equate with that logical link control sublayer of the data link layer. So your network layer receives this from the data link layer. The network then establishes the MTU size based on the media. So another terminology that you need to be familiar with is fragmentation. Fragmentation is when layer 3 will split the IP4 packets into smaller units based on the media. So if I'm going to go ahead and split my packets up, I have to make sure, based on the media in place, that my MTU size is equal to the size needed for the media. Okay, so this is a parameter that the data link layer has to tell the network layer. Fragmentation will cause latency. Okay? IP6 does not fragment packets. So one example is a router goes from an Ethernet to a slow WAN with a smaller MTU. When that happens, the NIC card has to make sure that it tells the network layer what the maximum MTU is if the network layer is going to perform fragmentation. So IP4 is the primary communication protocol for the network layer. So this course, even though yes, we are into IPv6 out there in the real world, we do concentrate heavily on IP version 4. So your network layer has many purposes. It ensures the packet is sent in the correct direction to the destination. And it is your routers that do that functionality. So your routers decide if they know where to send it, what exit interface to use in order to pass it along its path. So when we get to router, we'll talk about this little thing called recursive lookup. So what routers do, the very first thing they do is they unwrap that packet, they get to the destination IP address, they say, oh, hey, I can deliver this myself, or I can at least forward it to the next hop. A next hop in networking is considered the next router in sequence toward the destination. And this function happens at every single hop. So the first thing the router does is decide, can I deliver it myself? If I can't and I need to send it along, it then has to do this recursive lookup and say, okay, I know where it's going, but which one of my interfaces do I have to push it out in order to get it there? It contains information for network layer processing in various fields. The information in the header is used by all layer 3 devices that handle the packet. And again, the header information is simply source and destination IP. So IP4 network header characteristics include protocol header diagrams, or this is a protocol header diagram to your right that we're going to be looking at. It is read left to right and top down. It is simply providing a visual to us, the human network, for us to kind of discuss the different fields and try to understand what it is our devices are doing. So this is an IP4 packet header field. They will contain binary values of each field, which will identify various settings of the IP packet itself. They do contain several fields of information. However, you will only learn about certain ones. The most important ones right now in this particular slide are the ones in purple. Your diagram again is, read from left to right, 4 bytes at a time, or 4 bytes per line. And the two, again, most important fields are the source and the destination. So the 3 items in purple. So your version, again, is IPv6, 4, or IPv6. Source address, who is generating the information. Destination address, who is receiving information. Okay, so we will talk about other fields as we go along. So protocols have one or more functions. And so if we're going to define a protocol at this juncture, I'm going to say, let's talk about TCP. So if I'm talking about TCP, we're going to pay attention to other fields that we'll talk about when we get into TCP and UDP. So as an example, TCP, actually, hang on a second. I don't really want to talk about TCP right now, so let me just go forward in my discussion. And let's hit the next topic here. So this slide is just a description of those different fields. So be familiar with the version. The version field is going to identify whether we have version 4 as opposed to version 6. A 4-bit field will equal 0100. Differentiated services, these are used for quality of service. Okay, so a diffserv is a DS field, or the older intserf, which is TOS, or type of service. Those 2 parameters you will not discuss or learn about until Cisco 3. Excuse me. Your header checksum, that is your error detection. Okay, did this header or did this packet become corrupt? TTL is time to live. It is a layer 3 hop count. Right now, what I want you to take away from this is when it becomes 0, the router will discard the packet rather than having a packet just endlessly loop back and forth from router to router. But we will visit that again. Your protocol field is going to identify which protocol you are using at the next level. Could be ICMP, could be TCP, UDP, etc. And then again, your source IP address is a 32-bit source address, and your destination is a 32-bit destination address. The internet header length, the IHL, total length, and header checksum fields are used to identify and validate the packet. The other fields are used to reorder a fragmented packet, specifically the IP4 packet, which uses identification, flags, and fragment offset fields to keep track of the fragments. So those types of things are going to be inherent to an IP4. IP6 does not fragment. So IP4 has 3 major limitations. It became depleted. We have basically run out of IP4 addressing. There is also a lack of end-to-end connectivity, meaning we can't trace it from end to end. So to make IP4 survive this long, private addressing scheme and network address translation were created. So this ended direct communications with public addressing. It also increased network complexity because NAT was meant as a temporary solution and creates issues on the network as a side effect of manipulating the network headers and the addressing. NATing also causes latency and troubleshooting issues. So just to speak a little bit about NATing and not getting too deeply into it. What happened is there was an RFC, request for comment, that was developed, and it is number 1918. And within this RFC, it states a range of private addressing. So private addressing is something that I can address on my network on the inside of my own network. It is not routable on the internet. And we will talk about this more when we get to chapter 11. So in order to have a device on the inside network speak to or travel over the internet, it needs a public addressing scheme. So that is where NAT comes in, network address translation. So let me just write this up in a little clip shot here. So again, it's RFC 1918. And the range of addresses for A, B, and C, I know we talked a little bit about IP addressing, but just go with me on this. So an A has a range not unsimilar to a public range. It's got a prefix of 8, which means this is the network. B has a prefix of 12, and C has a prefix of 16. Now, I don't want you to get too involved with this at the moment, but what you might pick up on, for those of you who actually looked over the addressing stuff that I gave you, is for B and C, the prefixes are different within private addressing, or private addressing. So that means some of those are private and some of them are public, because 172 does fall in the range of a class B, and 192 does fall in the range of a class C. But this is more FYI than anything else, so I don't want you to get weighed down with this. This is just explaining why we need a network address translation. So you can understand if my little mom and pop, and I always like to use that so you know the limitations of things, my little mom and pop gets a class C. A class C only has 254 addresses. But mom and pop have grown exponentially, so now they need more addressing. So rather than trying to get a larger addressing field, they could use NATing in their network. And they could actually use this class A address, which is going to give them 2 to the 24 hosting addresses. Shouldn't ever need anything more than that, correct? So they could use NATing and get what they need within their network. So what happens is you have a network, and this is your inside network. And this is your outside network. So what we're going to define in NATing is you, the administrator, would decide how many of your publicly assigned addresses you want to give up. So let's say, as an example, you gave up 5 addresses, and you said anybody who needs to go out on the network, you can use one of these 5 addresses. So what happens is when it gets to a border router, so your border router is the router that lives in between your private network, and the public network. So we can say, as an example, this would be my border router. No, I'm spelling that wrong. Okay, this is where you would place your protocol of network address translation. So what will happen is the PC in our inside network needs to talk to somebody on the outside at a remote location. So they generate their packet. Now, when it gets to the border router, the router says, oh, hey, this is a private address. I can't send that out onto the internet. Let me look at my network address translation pool. So we have to create a parameter that tells our device what we want it to do. And that you will learn in either Cisco 2 or 3, I cannot remember which. Anyhow, that border router would take that private inside address and it, for the purpose of that conversation, give it or assign it a public address. It would then go out onto the internet to the destination, best case scenario, and upon its return, once again, when it gets to the border router, it is translated back into the private address and sent to the generating machine. At this juncture, that's what you need to know. So now just a little IPv6 overview. It was developed by the Internet Engineering Task Force, IETF. It did overcome some of the limitations of IP4. So some of the improvements that IPv6 made was increased addressing space. So it is based on a 128-bit address, not 32. It has improved packet handling, so it's going to have simplified headers with fewer fields. It also eliminates that need for natting. Since there is a huge amount of addressing, there is no need to use private addressing internally and be mapped to a shared public address. So as you can see in this graphic, it is 1 unidecillion, 10 to the 36. Okay, so that is a very large addressing space. I've heard it equated to, it wouldn't even address every single grain of salt globally on our planet. But that's just hearsay. I have no idea. But that's how large, that's to give you an idea of how large this addressing space truly is. It has a smaller header that is simplified. I'm sorry, the header is simplified but not smaller. The header is fixed at 40 bytes of information. An IP4 packet is 20 bytes of information. Okay. And that is largely due to the fact that IPv6s are 128 source instead of 32. There are several fields that were removed to improve performance. Some of the things that were removed to improve that performance was that flag field, the fragment offset, because again, IP6 does not fragment, and the header checksum. So again, unlike IP4, your routers do not fragment IP6. So again, as you see, very smaller header fields, So you still have your version, which is IP6. I should have noted in that last slide, guys. And be sure to change this yourself. On the IP4 header, it won't be either or. Um, and even now I'm looking at this, the slide topic heading is wrong, so I will change that. But the version is going to be IP6, and then your source, which is your IPv6 address, and then your destination, which is your IPv6 address there of the sending device, and the receiving device. So again, listing the significant fields, version again will be for V4 as opposed to V8, and that bit field is 0110. Traffic class is used for QoS again in that diff served, which is beyond the scope of this course. Flow label informs the device. So it's going to inform a device to handle identical flow labels the same way, and that is a 20-bit field. And we'll talk about, you'll get to flow labels in Cisco 3. Your payload length, this is the 16-bit field that indicates the length of the data portion or payload of the IPv6 packet. The next header is going to be the next level protocol, be it ICMP, TCP, or UDP. Your hop limit actually replaces that TDL field. And again, your source and destination is your 128-bit source and destination IP addresses. Now, IP6 packets may also contain extension headers, which provide optional network layer information. Again, they are optional and they are placed between the IPv6 header and the payload. Some characteristics are that they will provide optional network layer information. Duh, they are optional. And they are placed between the header and the payload. They may be used for fragmentation, security, mobility support, etc. And they are beyond the scope of this course. So I know I said there is no fragmentation in IP6, so don't get all wiggy about it. This is within a different parameter that you will learn about later on. And I know I say that a lot, and I do apologize, but you're here to learn the very basics, and then you break it down the further along you go in your studies. Now, packets are always created at the source. We know this. Who is generating what? Each host device creates their own routing table. A host can send packets to the following. I can send a packet to 127.0.0.1 or :1 in IP6. This is referred to the loopback interface. Pinging the loopback interface tests the TCP IP protocol stack on the host itself. So if you're troubleshooting, first thing you want to do is make sure you're not the problem. So you essentially ping yourself to eliminate yourself. Okay? Next, you want to ping a local host. Test the connectivity within your local area network. Next, here it says go to the remote host. For me, after I do a local host, I would also ping my default gateway. Okay? That way, if I know I can reach another individual in my LAN, I can assume I have connectivity within my LAN. If I can ping my default gateway, who acts as a host in my LAN, then I know that's good, and I can get out if I need to. Once I do that, I could ping a remote host. So again, a remote host are devices that are not on the same local area network. The source and destination host do not share the same network address. So in this example, after I go through router 1 to a remote location, that location is going to have a totally different network address. It cannot be 192.168.10.0. It would be something significantly different. So my source device determines whether the destination is local or remote. The method of determination is going to be within IP4. The source uses its own IP address and subnet mask along with the destination IP address. Within IP6, the source uses the network address and the prefix that is advertised by the local router. Local traffic is dumped out the host interface to be handled by an intermediary device, which is, that should say switch, not router. Remote traffic is forwarded directly to the default gateway on the LAN, which is usually the router's LAN interface. So I will change this on your slide, but let me change it here so you're not confused. So for our purposes at this juncture, your local traffic is handled by your switch, not your router. And again, we talked about this before. The way that your source device figures out whether it's going to local traffic or remote traffic is that ANDing procedure. Now, a router or a layer 3 switch can be a default gateway. Again, you will learn about that in your subsequent classes coming up. At this juncture, we talk predominantly about layer 2 switches. So, features of a default gateway. It is the network device, i.e. router or layer 3 switch, that can route traffic to other networks. It must have an IP address in the same range as the rest of the local area network. It can accept data from the LAN and is capable of forwarding traffic off of the LAN. It can route to other networks. If a device has no default gateway configured, or a bad or erroneous default gateway, its traffic will not be able to leave the local area network. So again, as an example, and again, when we get into subnetting and creating subnetting schemes, I will drill this into your head. If I have a network that looks something like this, okay? This is my switch, and this is my default gateway, this interface right here. Let's say it's F01. And on this side, this is my default gateway. For this network. When you configure and you go into your router and you go into interface 0/1, you give it an IP address and a subnet mask and the command no shut, which turns it on. When you do that, it creates an entry in the routers table. So when you do that, it becomes a host on that local area network. So this router is part of this LAN. This router, or router's interface, excuse me, is part of this LAN. If LAN 2 has an IP address, then all three of these, four of these, are going to have an IP address that starts with 172.16, including your default gateway. On this LAN, if my addressing scheme is this, then all four of these will have an IP address from this network. And just looking at this picture, I know that LAN 2 is remote because it does not have the same network address as LAN 1. Now, your host will know the default gateway, either statistically by the network administrator or, not statistically, statically, by the network administrator or through Dynamic Host Configuration Protocol, DHCP, in IP4. And again, we'll talk a little bit more about DHCP when we get there. But IPv6 sends the default gateway through a router solicitation. And when we talk about IPv6, we will also talk about this again. So either the router is going to assign the address in IPv6, or we are going to manually assign it ourselves. So at this point, I want you to start thinking of the terminologies: static as something that the administrators do, dynamic, the administrators create the decision, but then your devices manually take over. A default gateway is a static route which will be a last resort route in the routing table. All devices on the LAN will need the default gateway of the router if they intend to send information or traffic remotely. So in this example, both PC1 and PC2 will have a default gateway, or default route, to send all traffic destined to remote networks to router 1. And don't forget, when we do our static IP addressing, what are the 3 parameters that we need? Okay, static addressing. Definitely an IP address. Definitely a subnet mask. And I'm going to say possibly a default gateway. Only if going to a remote network. Okay, if you never intend to have communication outside your local area network, there is no reason for you to define a default gateway. Now, what they're showing you here on every PC, okay, all your PCs have their own routing table. So in this example, we're looking at the routing table for PC1. So you need to start to get used to understanding what these diagrams are showing you. So this is, excuse me one second. Okay, so when you're looking at something like this, you want to look at the very first line. That very first line tells you from whose perspective you are getting this information from. So this clearly tells me that I am in the root directory of PC1. Okay, and this is my routing table. Now your routing table has these lists. It has the network destination. It has the network mask, also known as the subnet mask. It has the gateway. It has the associated interface, and it has a metric. So when you're looking at this, would we all not agree that the very first parameter of the interface column is the IP address of PC1? Okay? The gateway, so when we start to do addressing, IP subnetting, what we tell you to do is when you start, you give your default gateway the very first address so that you know to remember to do that. So the gateway in this instance is .1 in the 192.168.10.0 network. So this is my default gateway, which is, let's say this is 1, this is 2, this is 1, and this is 2. Okay, and we can say that this would be F01 interface on that router. So your interface list is all potential interfaces in MAC addressing. Your IP4 routing table lists all known IP4 routes, including direct connections, local network, and local default routes. Your IPv6 routing table lists all known IPv6 routes, including direct connections, local networks, and also local default routes. So whether you're doing IP4 or IP6, you will get the same information. Now, when you're trying to look at this, you want to be able to understand what these addresses are. Okay? So I already told you in a previous slide that 127 is a loopback address. So anything here that starts with 127 is going to be a loopback address. So I can identify those first three as loopback addresses. Oh, I'm sorry, the first, or the 2, 3, and 4. This very first one we're going to find out is a default route. Okay, we talked about this, and you can see it right here. This is the network address for the entire LAN. Ten dot 10, again, is number one up top. 162, 168, 10.255 in that last octet for Class C is a broadcast. We talked about 224, those are multicasts. And lastly, when you look at a 255, 255, 255, 255, you should understand that these are broadcasts. If we were to continue and convert those addresses, they would be all ones, identify a broadcast address. So you need to stop trying to understand what you're looking at. Okay? On-link simply means it's attached. The interface, again, as you'll see here, is all 10.10, which is the PC in question. Okay? And then the metric is just a measurement of some sort. Now, what happens when the router receives the frame from the host device? So the first thing that happens is the packet arrives on the gigabit 000 interface of router 1. R1 de-encapsulates the layer 2 Ethernet header and trailer. So remembering back, in encapsulation, this is my data at the application presentation session. I then come down to my transport layer, and that puts a header of information, which is the source and destination port numbers. I then come down to my network layer, and it also gets a header. Then it comes down to my data link layer where two things happen. I not only get a header, but I also get a trailer. And your header is your source and destination maps. And your trailer is your error checking, which has that frame check sequence field, which holds that CRC value. So a router gets this information, and it has to unwrap it because what does a router use? I've mentioned this before. A router uses IP addresses to make forwarding decisions. So this gets to router 1. Router 1 unwraps it because router 1 needs to know what is the source and destination IP address. It's not the source, I'm sorry. What is the destination IP address? So it unwraps it. It gets the destination IP address from here, and then it has to re-encapsulate it. And it has to re-encapsulate it with new header for the data link layer and new frame check sequence. Okay, I need every piece of information. If I am missing one, that packet is dropped. So after it re-encapsulates the packet into a new Ethernet header and trailer, it forwards it to the next router in line. So there are 3 types of routes in a router's table. There is directly connected, which is a physical connection to your router. These are automatically added by the router, provided the interface is active and has been addressed. So that is you, again, going into an interface on the device, giving it an IP address, a subnet mask, and doing the no shut command. That will turn on the device and automatically create this directly connected route in that router's table. Next, we have remote networks. These are the routes the router does not have a direct connection to and may be learned either manually by us with creating a static route that would point to each one of these 3 networks, or dynamically using a routing protocol. Lastly is a default route. This forwards all traffic to a specific direction when there is not a match in the routing table. And we will talk about all of these before, but let me give you a brief synopsis of what they're talking about here. Router 1 has this network directly connected. It also has this network directly connected. Router 2 also has directly connected networks. It's got this one. Oh, I've got my little 2 over here. Oops, I'm sorry. I did not forget my little 2 over there. It's got this one, which they share, and it has this one, network 3. So router 2 has a direct connection to 3, and it has a direct connection to 2. Now, within dynamic, I would define a routing protocol. And I would say, okay, router one, you tell router two about what you know. So router two would create this update, and it would say, oh, hey, you know what? I know about network one. I also know about network two. Router two would get that information. And router two would say, oh, hey, you know what? I have a direct connection to network two, and I also have a direct connection to router three. So they would exchange information. Both of them would ignore the update that includes the 209 network because they both already know about it. But then router one will learn remotely about network three. And router two will learn remotely about network one. So when you are completely finished with updates, what you want to take away from this little descriptive is each router knows how to get to every single destination. We call this convergence. Okay, that is called convergence. Without convergence, routing will not happen. Now, I could create a static route for each one of these destinations because this is a very small network. And so, therefore, that wouldn't take me long as an admin. But understand, anything that we do statically, if it needs to change, we have to do that. So if my network starts to grow exponentially, I would have to sit there and create a static route to each destination and then stay on top of it and make sure that I change them if something happens. So in a larger network, static routing would not be conducive. We would go to dynamic routing. So within dynamic routing, and we will talk about this again, you assign a protocol to your router. Your router will then work dynamically without you and start to exchange these updates and share information and build their routing tables. Now, this last parameter here is what is referred to as a default route. Okay, it is also called a quad zero route. Because in order to configure it, it's this. The command, and this is not phonetically correct, I am just writing it to talk about it, is IP route So it would be in global configuration. This would be your command, IP route 0.0.0.0 space 0.0.0.0 space. And then I would identify the exit interface on the router or the next hop address. So in this example, from router 1 to router 2, This would be the exit interface on this router. The next hop is the address of the next router in line. So this is how you understand that. So that is a brief synopsis of how routing tables work and how they're created. So static route characteristics must be configured manually by the administrator, must be adjusted manually by the administrator when there is a change. The static route includes the remote network address and the IP address of the next hop router, which is the router next in line toward the destination. Great for small non-redundant networks, often used in conjunction with a dynamic routing protocol for configuring a default route. So this is how you see it here, as I did in the last slide. The command IP route, my destination network here is 10.1.1.0. My subnet mask 255.255.255.0. Both of those having to do with the remote network. And then in this example, I am utilizing the next hop address, which is 209.165.200.224. I could also have written this way, which is the exit interface. Now, dynamic routes are done automatically. You still have to go in there and tell your device which route you want it to use. I'm sorry, not which route, which protocol you want it to use. After that, your routers will start to discover remote networks, but again, initially, we have to configure it to say, hey, use this routing protocol. Your routing protocols will maintain up-to-date information. They will choose the best path to the destination. They will find new best paths when there is a topology change. They can also share static default routes with other routers. So it is very common for some routers to use a combination of both static routes and dynamic routing. And again, once we get more into routing, we will go deeper into these topics and actually look at your routing tables. I believe in chapter 10, module 10. So when a router is manually configured with a static route or learns about a remote network dynamically using a dynamic routing protocol, the remote network address and next hop address are entered into the IP routing table automatically. Even though you have to configure a static route or configure a routing protocol, once you do, it automatically populates into your routers table. So again, with regard to perspective, I am looking at the routing table from the perspective of router 1. So on router 1, I issue the show IP route command, which is what I utilize in order to see its routing table. So an L is a directly connected local interface IP address. okay? So that means 192.168.10.1 is this router's interface. The other one, 209.165.200.255, or 225, excuse me, is this interface on the router. Those are your link local. So your link local identifies the directly connected interfaces. Next, we have a directly connected network. So this identifies the network in totality. So here I have, again, two directly connected networks. I have the 192.168.10.4 and I have the 209.165.200/30 network here. So those are the entire networks that are connected. Thirdly, I have a static route that I created as the administrator. So my static route is here. And we'll get into a little bit more as we go along what exactly does this default route do. When you see a static route with an S and an asterisk, it means it is static, but it is a candidate for default. That is a quad 0. Would you not agree that this is a quad 0? Okay, so that's the third parameter here. There is an O for OSPF routing table, and they could also use, I'm sorry, so in this instance, we are using OSPF as the routing protocol, or if there is a D, it would be EIGRP routing protocol. So in this circumstance, we are using, something different here. We are using OSPF. Okay, and within OSPF, we are advertising a network, or learning about, not advertising, learning about a network. Okay, so they're learning about the 10.1.1 network remotely through OSPF. However, I'm going to correct this slide because it is incorrect. They're talking about the 1.1.10 network via the interface of 226. So on G001, which is on router 2, except the network that is attached to router 2 is 10.1.2.0 in this picture. So do not get confused by that, please. There are reasons why, but I'm going to change this because I don't want you to get confused. There are reasons why it's up here 10.0.0.0/24, but when we talk about module 11, that'll make more sense. What you need to take away from this is understanding this routing table.